good to go.
All right. Hi guys, I am Kapil, and today we're gonna be talking about intro to self-driving cars. And here's a little background about me. I am a founder of Taskmate, which I explained a lot about on a previous workshop, which was like an hour ago. And I go to University of North Texas. I am a deep learning natural processing researcher, and I'm a software engineer at Wax Foundation. I think, and then the most relevant to this talk today is I'm a perception engineer at Team Capers, which is a team where we're competing for the DARPA Subterranean Challenge, which is essentially we're trying to build an autonomous cave robot. So I guess the similarities between an autonomous cave robot and an autonomous car is they're kind of similar, but there's like a lot of things that are just like new to cave robot, which is like things like you have to worry about a lot more things. Like for example, you have to worry about like rocks. You have to make sure your I guess your robot is built in a way that can handle going through small rocks and also big robots, and yeah, that sort of thing. But right now I'm going to talk about self-driving cars. Right. So on the screen you have like a general architecture what a self-driving car looks like. And so you have sensors. So you have camera, radar, lidar. Lidar, I'm going to go into depth in here in a second. Then you have GPS, and then you have like other sensors. And then these are kind of like your inputs. And these inputs are kind of passed into this perception module. Perception module is kind of just there to um, just detect things that are around you, around the car at any given moment, and then also detect like all the other things like such as lane detection, like if you're going in, detect where the actual lane is and where you actually stay, and traffic light detection, so like finding out where the traffic light is in a given camera input and like radar and that sort of thing. And then we also have to classify what traffic light is in order to figure out if this is a red light, green light, yellow light, if you have to go on, stop, that sort of thing. Then we also have a traffic sign detection and classification, detect if there's a traffic sign, and then classify it into our list of traffic signs in order to find out if you have to actually worry about anything at that given moment. Then we also have object detection tracking, and this object detection tracking kind of object basically here means other cars. Maybe there's someone on their bike on the road. Maybe there's like people crossing the road. It's basically anything that's like moving on the road. And then we also have like tracking, because we have to track them like we have to make sure like our path does not coincide with their path given their velocity and our velocity. So we have to keep track of them in real time to make sure, yeah, we don't crash into other people. Another thing is free space detection. Free space detection basically looks into where's like free space we can kind of go into. Like for example, there's like a car to your left. There's like a space in the middle of that car and another car to your left. So that's free space. That's something you can go to the left, and you can take over that free space. And then we have this thing called localization, which I will go into depth more on our next slide. And like whatever you learn from perception and that sort of thing is passed into planning algorithm. So the planning algorithm is there in order to actually plan out the route and like every single thing you need to do. So for example, route planning. Route planning basically means exactly where you're going to be in, let's say, 2 seconds. This is the XY coordinate at this speed. You need to be at that coordinate. Prediction and behavior planning is kind of looking into the perception module, like the object tracking kind of thing, kind of goes into that. What it basically does is it looks at other cars or other objects on the road and detect if tries to detect if our route kind of coincides with their route, and if that occurs, then we either need to speed up or slow down, that sort of thing. So behavior planning kind of goes into if we're going to crash into, if we keep continuing down our path, are we going to run into anything, and if that occurs, we need to do something. And then control is where that do something occurs. Like all these over here, we're just kind of taking input, learning about like kind of environment, and planning over here, we're kind of planning on what we're going to do. Control is actually like what you're going to do. So PID and PC, these are like different type of controllers I'm going to talk about in a little bit. But the main idea is control is what actually does something. Like all of this is just computing. You learn this one's a sensor, just takes in data, perception, learn about the environment, planning, plans the next course of action, like next place to go. Control is the actual one that press the accelerator, turns the steering wheel angle, brake, like just like 3-4 inputs like you have in every car: brake, accelerator, steering wheel. Yeah, those are kind of the main ones. Now let's look at perception over here. So perception is just used to perceive the environment in essence, just like road signs, traffic light detection, classic lane detection, pedestrian drivable area. I kind of went into depth on it the last slide, but I guess the main idea over here is perception is perceive the environment, just like look, find out what's in the environment. And one thing I did not talk about was lidar. Lidar is basically, it stands for light detection and ranging device. So what basically does is it fires out like light, in a sense, like millions of rays of light in order to create like this three-dimensional map of the surrounding area. And this is what the map kind of looks like. And this is like best case scenario, right? The problem with lidar is that it's almost never like perfect. It cannot never perfectly detect every single object or every single object in that area, right? And then we have like things like point clouds, features, and grids. And those are point clouds and features and grids are basically ways we can take that three-dimensional map and turn it into 2D map, which we can use to compute, which we can then use to, which we then use in our planning algorithm, right? So I guess one more thing about lidar is it's kind of a controversial topic in like the self-driving space. There's some companies that like lidar, we use lidar, we use lidar. Then there's like companies like Tesla, for example, they do not use lidar. And I guess the idea over here is that, um, like Tesla, what they say is that we do not use lidar because that's not predictable 100% of the time. So what Tesla does is they just use camera input. They do not use lidar. They just use camera to create their own maps in essence. While Waymo, for example, they use lidar and that sort of stuff. And I guess while I'm at perception, I'll also talk about how like different car companies have like different approaches to stuff. Like everything, like every company, basically, they need a map of the area. Like today in like state-of-the-art technology, most companies, they need a map of the area before they actually launch an area. So I'm talking about Waymo, for example. They need to send out like 3 or 4 like cars that are attached, like they have like sensors and like cameras all over the place, and they drive that around like every intersection of the city, for example. They keep driving that around, and those sensors are kind of just taking in data and creating a map for creating like a lidar or like any type of map for like their car to use when they actually launch their autonomous vehicle in that area. So yeah, so that's a little about like mapping how like people cars, like they need most cars these days, they need like people to go in beforehand to kind of map out the area before they can actually launch autonomous cars over there. So that's a little tangent I'm going in, but let's talk about sensor fusion a little bit. Sensor fusion basically means you take in like multiple cameras, like camera, lidar, and those things, and you kind of fuse them in order to come up with a better prediction. So let's say like you missed something in lidar. Well, if you miss something in lidar, then if you're just using lidar in your software, if you let's say you're using lidar in your software and your lidar at that given moment misses a car, that's going to mess up your planning algorithm, which is then uh, going to mess up your control algorithm. So you're just going to crash into that car. But sensor fusion is kind of there in order to make sure that scenario doesn't occur. Sensor fusion basically means we look into camera input and also the lidar input, for example. So you just look at multiple sensors input and then kind of create a prediction of what actually is occurring based on sensor fusion. So that's just like machine learning algorithm, kind of just take in multiple sensors and create like a one story of what's around the vehicle. Then there's also this thing called localization. Localization basically just means finding the exact location the car is based on like other objects in the camera input. For example, like you have so localization basically means it takes in GPS and the camera in order to find the exact location on a GPS, for example, of that car at any given moment. And that thing is important because you also have to follow a map, that sort of thing. And if you're just using like GPS, for example, it's going to be hard for you to detect exactly where you are. When you're using GPS plus camera, you can detect, let's say you're in the right lane on like this road. And that's very important because we also have to make sure we're following the right path. And just using GPS won't give you the best prediction of where you are. You have to use localization in order to actually predict exactly where you are at any given moment. So let's look at a lane detection algorithm. This is just an example. You guys don't have to copy this code. I'll drop a GitHub link, but it's just a normal GitHub. So you take in, so you have like CV2, your NumPy, all these functions, you pass them in, and you don't have to worry about it. These are just like putting stuff. And then this right here, media problem two, sounds like before, it's just a video of a car, like a dash cam on a car. And what we're trying to do in this function is find detect lanes. That's all we're trying to do. Detect like white lines and figure out like the exact lane. So over here, there's really not much to worry about here. Like frame, we read frames, image. These are just like normal CV2 stuff you need to do. But I guess the main thing over here is the main thing we have to worry about over here. There's is like this line thing, lines.cv2 on the second image, lines.cv2 lines.p. So this is kind of the main thing. And I guess the idea I'm trying to show with this algorithm is basically you don't have to like code out like from scratch every single thing. There's like for especially for perception, like there's like 10 things over here, like lane detection, transfer light. There's you can use other libraries that actually do that for you. So a lot of times you don't have to physically code everything out, and you can just use libraries like CV2 and like PyTorch, TensorFlow, and all these libraries to have like a built-in function that actually detects those things. So the idea I'm trying to give over here is that you don't have to go through, you don't have to rebuild every single thing, and that's actually very important because when you're like actually building a self-driving car simulation or like even a physical one, there's like a lot of things you have to worry about, and doing everything from scratch is a bad idea. It's a very bad idea, and you need to um, use already built code when you can. And just as a sort of demonstration, I'm gonna run this code over here. So I have this, I can drop a link to the repo in chat. This is the repo look like. You guys can look at it a little bit. There's not much going on over here. All you have to do is just clone the repo, lane detection. This is the one. Just clone the repo and just run the code based on like image. Image is already built in there. So if you guys know how to use like Git, for example, it's just going to be git clone and that link I just sent you. So I guess you don't have to worry about that. You can look at it on your own time, but I'll just show you what it's going to look like after you run the algorithm. So let's go to lane detection. And I created like there's like a function on here that basically creates video of the object after detecting lanes. So let's run that video. And yeah, this is what kind of it's going to look like. So you can see over here you have kind of like green lines kind of detecting lanes, and then you can also notice like sometimes it just like right at this moment like it shows like green line on the side, so it's detecting there's the lane is actually on the grass side. So I guess the idea over here is that sometimes it's not fully predictable, and that's kind of a problem in self-driving cars right now. Is like sometimes it just like some messed up sensor input can like mess up your whole algorithm, and you can crash into a car. And I think that's still a problem we're trying to figure out in like self-driving car research and that sort of thing. But this is what the algorithms kind of look like for lane detection. Yeah, and that's all kind of the whole idea of like showing this lane detection was I just want to like the whole idea was that I wanted to show that you don't have to rebuild every single code for every single algorithm in there, because that's going to take long time. And the idea is always use built-in libraries in order to make your code kind of go faster and that sort of thing. So now let's look at planning. So now, like the perception module, all it did was pass in. There's a car over there. There's free space over there. There's a red light. There's a red light in front of you. There's some free space to the left, and that sort of thing. Now, planning is actually going to take all that input and develop a plan for the car to do. So what's going to do is going to plan the exact route the car needs to take at any given moment. So there's like multiple different approaches to this. One is like there's like many different approaches, like many different companies and that sort of research, and that they look at it in different ways. Like one is like model all possible trajectories of a vehicle. So like you model every single possible trajectory that you can take at any given moment, and then have like a cost function that decides if this and then given the cost function, whichever possible trajectory gives the best value in the cost function, do that. That's an idea. And that one looks into more mathematical models. But a lot of people also use data-driven clustering. So basically what that means is you have like a huge amount of data on how like cars react, or like how cars like use their trajectories, like how they turn left, how they turn right, how they keep going straight, and what they do in a particular scenario. So this one's like fully data driven, like you use data and then you have like an unsupervised learning algorithm running to predict the best sort of action to do, best sort of planning module, that best sort of path the car needs to take, right? And then the path planning itself, this one's kind of just modeling how it should do it in a sense. Like it's also like multiple approaches. This part, model trajectories. This one's kind of looking at other cars too, because you also have to think about like you're not the only person on the road that's actually moving. There's other people in other cars that have their own autonomous algorithm, and that doesn't have to be like an actual autonomous algorithm. They can be like a person's brain. They're also they're trying to go to a particular place. They also have their own planning. They also have their own path they're taking. And you also have to make sure that as soon as their path changes, and like depending on how their path is, you have to make sure you don't crash onto them. Like that's not going to be a problem if all cars like this, like looking at other cars won't be a problem if everyone just follows a straight path, but that does not occur in the real world. So what happens is we have to make sure we're tracking all the cars' movement in order to predict where those cars are going to be in a given amount of seconds. So we need that in order to plan for our trajectories and make sure we don't coincide. Now the actual path planning is just a search problem. So now you took the perception module and like the point clouds that talk about features, grids, and that sort of thing, that kind of turned that 3D space into a 2D space now. And now that's now like basically a list of grids. So it's just a search problem. In essence, you just turn your 3D world into a 2D set of grids, and now it's just a search problems. And it's kind of like a maze. You can think of it as a maze, and the maze is you have to get from point A to point B, and there's like a lot of grids are kind of blocked off, and those blocked off grids basically mean either that's like the end of the road, or there's a car right there, right? And so given that at any given moment, it's just a search problem, right? So you just have to optimize that search problem, best closest scenario, given that. And I think over here, like the whole path planning, or like the planning algorithm, is just return an xy point with a velocity for every z seconds. So basically what that means is the whole point of it is to return a key point, or like a point in like the 2D space, or that the car needs to be at any given second, and that car needs to be there at this velocity. So it's just telling you be at this point at this speed at this second, that sort of thing. So that's what it kind of returns. And this we need to like kind of break it down to this for the controls algorithm to actually be at that point. So we need just the xy point velocity, and that thing is given every z seconds. So a lot of like solutions in the market right now is people do like half a second, 1 second, 2 second, that sort of thing. But it really depends on what works well for that particular car. So yeah, just the idea over here is that the planning algorithm returns a point that the car needs to be at this second and at this speed. So it controls. So control is kind of our last kind of tier of I guess defense in a sense, because this is what like not if your controls algorithm does not work well, it doesn't matter how well your other algorithms are, because controls is the one actually does something on the 3D real world. So for controllers, we have for the controls algorithm, we have different controllers, right? And those controllers, all they do is change one of these three things, right? Either the steering wheel angle, the accelerator, like they press the accelerator, or they press brakes, right? There's only kind of three main things you can do, like in a car, and those are the thing that it controls. Now, PID and MPC are just different types of controllers, and by controls I mean different approaches of actually finding the best, being able to actually perform the path given by the path planning algorithm. So these are just different approaches. So let's look at PID. PID is basically, it's called proportional integral derivative. So what it does is it just basically has this error module. And so it's just the error, it just calculates the error, and it calculates error based on what's the plan. So what is the plan? Which point do I need to be in? And then it compares that to the result. The result is basically where am I actually at. So plan is where am I supposed to be, and result is where am I right now. And given that, we're trying to minimize error and follow the path. Just follow the path. Yeah, we're just trying to minimize the error, which will help us follow the path given by the path planning algorithm. And the thing with PID is that it's one of the simplest one to kind of put together. But what's kind of wrong with that, which I'm going to show in a second with the simulation, is it's not it's not very perfect in following the path. It's going to follow the path, but it's a lot of it kind of oscillates a lot. It kind of goes to the left because it tries to follow the path and tries to correct itself. So it's a lot of like oscillating. Like if there's a path right here, it kind of just follows, tries to follow it, and that might not be the best approach. But that's not the best approach, but definitely not the best approach. But when you're trying to, this is the most simplest to put together. So when you're like building a self-driving car, you definitely need to first put together PID, because that one's like definitely first thing to put together, and that's always like helpful to put together like the minimal thing you can do, and then worry about like complicated other stuff, because this will do the job. It won't do the job the best, but it'll do the job. Next, we have model predictive control, which is the most complicated to put together. And the reason behind that is model predictive control kind of looks into physics of the vehicle. By physics, I mean the weight, the size, width, length, like for the vehicle itself and also other vehicles. So the thing what happens over here is the PID is kind of bad at following the path perfectly, because it does not take into account the physics of the vehicle. So how heavy it is, or how long, or how the length and width are. And that is a problem because each car is different in size, different in weight, different in height, different in length. And using the same algorithm for each car is not going to work, because let's say you have a heavier truck, for example, right? And then you use the same amount of turning right, you use the same steering wheel angle and same accelerator to turn right, right? If you use the same as any other car, any other small car, it's not going to turn fully well. You're going to probably hit a curb on the left side if you try to turn right. And let's look at the opposite scenario. You're using the same algorithm for a much smaller car, and the algorithm is kind of trained upon much heavier vehicles and much bigger vehicles. And if you use the same steering wheel angle, accelerators, and same algorithm on a much smaller car, it's going to overturn. So it's going to hit the curb on the right side if it's trying to turn right. So that's why MPC is kind of the best case scenario right now, because it looks at the physics of the vehicle. So it kind of changes itself based on the mass of this vehicle, and also kind of make sure that we're not going to crash into other vehicles that are like a particular length and size. And so but the problem with MPC, model predictive control, is it's really good algorithm, but it's just very difficult to put together. It's also very it's a very big research area in controls, and MPC, like PID, are kind of like people still research PID, but mostly like model predictive control, because it's just very difficult to put together in the actual self-driving car. So that's why most people, when they're building self-driving cars for like competitions or for just like companies themselves, they start with PID. They'll always start with PID. It's the simplest thing to put together. And MPC just, it takes a very long time. It's always to put that, like do that next. Next, we're going to talk about simulation. So the thing with simulation is it's just a way to test self-driving car software. The problem with having just hardware, the testing a physical self-driving car is you can test it, but there's like so many things that could go wrong. Like let's say if you have an actual car that you're testing with like putting sensors on top of the car and that sort of thing. There is like if the car crash, like for example, which is going to like 100%, it's going to crash. The first time you test it, it's going to crash. And when that happens, it's going to break your camera gear and then you have to replace them. So it's like a whole different scenario. It's going to cost a lot of money and that sort of thing. That's why a lot of companies, except for Zoox, which is like an Amazon company, which is building urban driverless cars for like urban drivers. So you just sit in and go. So what they have is they have a big simulation problems going on. So what they do is they just take their car, just build a simulation around it, build a simulation exactly what the real world will look like at any given moment. And they just run their software on the simulation. And so the thing with that, they can test like millions, even billions of different driving situations and scenarios in a very small amount of time. And that's helpful because you'll never know every single scenario that can occur in a self-driving car. You just won't. But when you're testing it like millions of billions of time, it's kind of sort of, you can kind of understand the basic trend of how self-driving cars, like trends or like how, what scenarios you're going to run into. Scenarios such as someone jumps in front of your car. Scenarios like there's a car that kind of steers to the left right in front of you at a given moment. Like those scenarios, they're really hard to model in real world, like physical hardware. So it's always best to use simulation, especially if you're a software person, you just want to build like algorithms. You have to work on simulations. Those are really helpful. And I guess the main one I'm going to talk about is Carla. Carla is just basically a Python C++ based simulation, which is like a lot of people use it. It's like really helpful in building software and that sort of thing. When you're building it for a company, however, like you have your own simulation, but like for just like software developers in general, most people just use like these such algorithms like Carla, for example. So right now we're gonna run one of the simulations using the two predictive control algorithms. So I'll drop the GitHub repo in Zoom chat. Oops. So this is kind of what the repo looks like. So I guess you don't have to worry about a lot of things over here. Like I guess you can look at it yourself. Like you go to edit settings and you can change settings on pi, train on pi. A lot of it is like kind of built in, and then controllers are kind of already coded into. They have like two different controls in there. So you can play around with that. I've already trained it on here, and I'm not going to train it again because I don't have like GPU connected. So it's going to take like 15 minutes to train it. But I trained it beforehand, and I do have a video you guys can see in order to see what the simulation actually looks like. And so let's go to that folder. And so, you guys remember the two controllers I talked about? One was PID and one was MPC. So right now I'll just show you the difference between the two and how the car kind of changes depending on which one it is. So let's run the PID first. PID run one. So this is what it's going to kind of look like. So see over here, the car is kind of following the path, but it's kind of oscillating a lot. It's going to the right and left, and that's because it's always trying to correct itself. Because it's just always trying to correct itself, and it's either going to overcorrect or undercorrect. So you always have this like oscillating shape going around. So this is the PID controller. And it's going to do the exact same thing. So it's going to keep oscillating. And the reason behind I already explained was it doesn't look at the size or weight of the vehicle, which is a big thing. It just does the same algorithm for every single vehicle, which is not a good idea because Each vehicle have their own mass, own size at any given moment, right? So that is the PID controller. Now let's look at MPC. MPC supposedly is supposed to be better than this one. Let's see how MPC does on the same exact map. So here it is, MPC. As you can see, it's not oscillating. You can see yellow is the path and green is like the current path like it's taking right now. So you can see it's like following it very well. It's not oscillating like the PID. It's just following it exactly. And like I would explain, the reason behind that is it's looking at the physics. It's looking at what's the weight of the car at the given moment, and changing the pressure, like steering wheel angle, changing the pressure to apply on the accelerator, the brakes, and that sort of thing based on the weight and size of the vehicle at any given moment. And that's why MPC is kind of bigger. So I just wanted to show that algorithm. You guys can kind of go around, mess around with Carla. Now I didn't go too much into it, but you guys can go around and mess with this. It's pretty important, and you have like graphs that show like trajectory and that sort of thing you can look at. And then the last sort of thing I wanted to talk about is like next step and resources. So I think what's happening is, the thing with self-driving car is the best way to learn it is learn it while doing. So learn it while you're actually building even a physical self-driving car, or even a simulation like I talked about last time. So and there's like a lot of research for this, like the Waymo dataset, and that they just released, I think it was a week ago, they released like a ton more of data sets. So those data set include like stuff like everything, like they have like, I heard there was like a statistic, like they had like um, thousands of hours of driving camera input for you to use, and anyone can use it basically. So that is a good place to start if you were looking for a data set. But I think like self-driving cars are a very team-oriented thing. Like you always have one person working on, you have like a team working on this, you have a team working on perception, team working on the hardware, team working on simulation, a team working on controls, a team working on planning. So it's a very team-oriented activity. And then like recently there has been a lot of change in like North America. For example, there's been a lot of like self-driving car teams that are being created in North America, and those are like college-based. So one of the ones I'm like most familiar with, in this MIT driverless, they have um, like a team base over there, and it's not just for MIT. For example, you can apply to that. They have like a lot of people from other universities and that sort of thing. So definitely check that one out. And that was not the only thing. A lot of universities, I know, have them: Carnegie Mellon, UC Berkeley, Stanford. They all have like self-driving car teams, and those are built like by college students for college students, and they just there to build autonomous cars and compete. And by competitions, I mean these are kind of the three main ones right now, like in the Autonomous Challenge, which is just basically like multiple teams kind of come in and then they race on a race course. And that one's like actual race course. You don't have to worry about traffic lights and all that sort of stuff. But you do have to worry about, it's like NASCAR. You just have to worry about going the faster on the track, and not hitting any other vehicles, and not also, there's also like points in a sense, like if you go through this part of the map, this like coins in a visual space which you're given like coordinates of, and if you get those, that's like a point. So those are kind of what they are. In the Autonomous Challenge is like a big one that's coming out, it's coming up pretty soon here in a couple of months, that most car teams are going to. And then there's also Formula Student. This one's more like international, like Formula Student Germany, Formula Student Europe, like those places. But that's also a lot of like United States team go to this. Another was like Robo Race, which is essentially the same thing in the Autonomous Challenge, but the difference is they do it like every month or so. Because the thing about self-driving cars, like they're constantly changing. It's not like you build one and then you just run that in every single one. No, you're gonna improve every single month, right? There's always improve, and they're going to keep improving. Self-driving cars are going to keep improving until at least we hit a level 5 autonomous car, which basically means a fully autonomous car that can do everything, that can take you from point A to point B without crashing into anything at sort of any sort of like physical barrier, such as the weather. Like like it can go in like rainy weather, it can go in like completely dark weather, and that sort of thing. So the idea behind it is like there is constantly improving. And then if you guys want to, I should reach out to like different teams. I know a lot of universities has them, So maybe even your university has them. If you look in, you probably find something. And if you don't, you can always like create one in your own school, in your own university, like create your own team. And like a lot of teams are just starting, so it's not like you're going to be really behind if you make one in your own thing. And I guess the like actually creating a self-autonomous self-driving car team is actually kind of difficult, especially because like this thing, like so many things that have to go into it. And I think like a best case, like one of my friend kind of described it like self-driving cars are basically, it's just basically they're very difficult to put together in a sense. Like you can put software together, but actually turning the software into the hardware is like, it's a planning nightmare. That's what it is. It's just very difficult. So you always need like a, so the idea is you need a team if you're actually going to do these kind of things. And you can always create one. And if you're actually going to create one, I would suggest go to like MIT Driverless like YouTube channel, and they have some resources on there on how they started, which is I think those are, this one's like we're the most built team. Others are just kind of starting. This one's kind of been around for like a year or two. And so when you're creating, just like they have some bunch of resources you guys can try and that sort of thing. So yeah, so I guess the uh, action item over here, if you guys want to, you guys should try out, look for driverless teams built for college students. And I think I found those. I'm probably going to join one soon too. Those are just a good way to kind of learn more about self-driving cars and also be part of a team to work on something new and innovative. I think that's a great, like I find that very interesting, like college experience and that sort of thing. So yeah, that's something. Yeah, that's all I had for you guys today. Thank you for coming. And if you have any questions, feel free to drop it in chat or unmute. Right. Great question. So you're asking what part of the world are actually implementing these cars on the street and how widespread is it? Right. I think it's becoming like more and more prevalent like every single day. Like for example, Tesla is the biggest one. They're not fully autonomous, but you can call them like decently autonomous. Um, they're like Tesla is like they're increasing like all the time around. I know China is very big on self-driving cars too, and I'm pretty sure Europe is also very big. Like I think the most it depends on your definition of self-driving car. Like for example, Tesla is technically a self-driving car, but you technically need to be in the car in order to make sure everything's going well. It's more like driver assist. Driver assist, for example, is getting bigger and bigger. Driver assist basically means staying in the same lane. That is becoming more, it's like very widespread right now. Like every company basically has a model, a car model that does that. Fully autonomous car are not are not fully there yet. Like we're not like in technology aspect, we're still not fully there yet. So you won't find them very widespread. So driver assist is widespread, like you'll find them everywhere. A fully autonomous car is kind of hard to come back. Like a fully autonomous car, I would like for like Tesla. Tesla is the kind of one of the biggest ones. But even Tesla has like their own things. Like you cannot, you have to be paying attention in the car. Otherwise, like the car is going to slow down and it's going to stop. Like that's part of their algorithm because they know the car cannot go fully autonomous like for a long period of time and that sort of thing, because it's still in kind of research area. And I guess the biggest one kind of here is Waymo. Waymo, what they're doing is they're going full out. They have just a car, no nothing. You open their app. You it's like Uber but for self-driving cars. So they just open their app, ask for a ride, the car comes, you sit in the car drives itself like fully. That's what I would call a fully autonomous car, right? But the problem with them is they're not like everywhere, because the reason is they have to, like I talked about earlier, they have to actually map out an area before they can launch in it. So I know they're in a couple different areas and they're working on mapping out other areas too. But the problem with that is they have to like spend weeks just sending multiple different cars with people in them, mapping out the city in order to actually launch over there. So the answer to your question on like how widespread it is, it depends on your answer to a self-driving car. Um, Technically, a driver assist is also a self-driving car, which kind of assists you in a sense. But if you're talking about full autonomous cars, they're not that widespread yet. But it's still working on it. And for the future, I think I have a feeling like a lot of people I think say that it's just going to be one company game. So like one company just gonna take over the whole market. And I kind of disagree with that. I think there's going to be like multiple different ways self-driving car is going to be. Like, for example, like Waymo is going to be just Waymo is just going to be like a taxi in a sense, a self-driving car taxi. Tesla is going to be, you can have your own self-driving car which you can take anywhere. Then there's Zoox, which is just for like urban drivers, so going through like an urban terrain. Then you have this company called Too Simple, which is basically trucking. Trucking is a very big thing in self-driving cars, where because like there's like a lot of trucks on the road at the given moment, and if you can make that autonomous, it's going to be very helpful, like saving cost, saving money, and all sorts of things. So trucking, I see like all these different kind of things going around and making the future of self-driving cars. And last thing I want to talk about was Comma AI. Comma AI is basically, if you want to describe it as, it's it's kind of basically what they do is they don't sell cars, they sell a sort of device. A device basically meaning like kind of a device that has like a bunch of sensors, cameras, and that sort of thing. So basically, what you can do is you can buy that, you can put it on top of your car, and you can make your own car self-driving. So I think that is going to be pretty like prevalent in the future. I think that's going to be big. Like I don't think that's going to be big in that sense. I think it's going to be a good kind of introduction for the world to self-driving cars, right? It's easier to kind of add something on rather than replacing a car itself, right? It's easy. It's easier to buy a device for $1,000, put it on top of your car. Now you have a self-driving car. I think that's going to be a bigger thing in the beginning, but of course, in the end, I feel like Tesla and Waymo like have it right. I think it's going to be more of a taxi. It's going to take car ownership away and that sort of thing. So I think that's what I think the major feature of AI, self-driving cars is through different companies trying complete different things. And then I think it starts off by Comma AI, them just turning your own car into a self-driving car. Yeah, thank you. And Jason, how can I start learning about self-driving car algorithm? What technology do I need to know first? Right. So I would say the best scenario I would say was like for me, what I learned was try going through like a course, for example. I know Udacity has like a 900 degree on self-driving cars that kind of goes into that's a pretty good thing. And then the thing with self-driving cars is like it involves a lot of C++ and Python. So I would say get a very good understanding of C++ and Python, and then take one of these like Udacity 900 degree on like or like other kind of sort of like certifications or like things you can learn from there, and then you can kind of go after you have like a decent good understanding. I think the best thing you can do is learning while applying. So either you can apply to internship at one of these like companies that are just building, or you can like I talked about one of like self-driving teams built for college students. You can try one of those. So I would say it was the first thing to learn is definitely C++ and Python, like be really good at them. And after that, I mean, of course, you need to get like a good understanding of deep learning, AI, machine learning. Those are like definitely need to know about those. And after that, because like the whole self-driving car thing, it involves AI, machine learning, like everything, like every single part of it is that. So you need to have a good understanding of how all those works. But there's also a lot of things that are just specific to that. So I would say was make sure you have a good foundation for Python, C++, AI, machine learning, deep learning. And then after that, I would say do like a course or something in, I'd say Udacity degree is a great one on like self-driving cars particularly. And after that, I would say like don't try to learn while you're doing it. So try to learn while you're either like doing an internship at a company where you're working on something, or like I talked about a self-driving car team at like a university, which you're building towards. Yeah, it's a very iterative process. And then like self-driving cars, they're not fully out yet. So I think I found it kind of interesting because it's not fully developed yet, and you can be part of like development of a fully self-driving car. So I think that's what I find pretty cool about this. Yeah, that's what I would say how to start learning about stuff. Let me know if you have any other question. Right. That's a really good question, Ryan. I think like for me, I think what's going to happen is that if self-driving cars will make roads safer or more dangerous, I think that really depends on how many cars are on the road, right? So the thing over here is the problem with self-driving cars, like if we, let's say, launch self-driving cars, there's no way in the beginning every single person is not going to have a self-driving car in the beginning. There's no way, right? Only a only a percentage of the population will have a self-driving car, and the problem with that is, driving tends to be like, what I've learned is driving tends to be a very um, social process. Like when you're driving, you kind of look at other cars. You look at person. Let's say a car is passing. You kind of look at the person to make sure either that guy's going to stop or that guy's going to keep going. And based on those small kind of interactions, that's how you make your decision, right? Well, self-driving cars can't do that. They cannot just like look at a person, and the person cannot look at this. I mean, they can kind of look at it, like you can attach a sensor, like a camera, to look at like people's faces and detect where they're going, but the person cannot look at a self-driving car and say, okay, this one's gonna he's gonna turn left and that sort of thing. So in the beginning, I think it's going to be a little bit dangerous in a sense, but I think when it's going to like the actual results of self-driving car that makes the road safer is going to come when there's a large concentration of people that are actually using self-driving cars. And so when that occurs, everything, most of the cars are self-driving cars, and that's going to make the road safer because everything's kind of robotic in a sense. And there is actually a caveat to that. The problem with that is intercar communication. Yeah, that's exactly what I was going to say. Um, the thing is, like, if you have like multiple different types of self-driving cars coming, it's going to be if you can have like communication between those cars, it's going to really help with like communication. Like, so I envision like the best case scenario would be there to be some kind of self-driving car law, or like a society, or like a like government based something that enforces laws that basically what it means is every single car on the road has to be connected to has to be able to talk talk in a sense to other self-driving cars on the street. And I think that will be like a huge thing in making roads more safer, because if you can talk to other cars and detect, okay, this car's going there, this car's on there, all in like just one database, and that's going to like really help with making roads safer, because you know exactly where other cars are going if you can talk to them, like if you have like if you're on the same database, that sort of thing. So I think, yeah, inter-car communication is like going to be really big. And yeah, it really depends. Excited for the future. But really great question, Jason. If you have any more question, feel free to drop them in chat. How do we prevent being hacked? That is a great question. Okay, I think that kind of goes into cybersecurity. And in today's day and age, you cannot code anything to be unhackable. It's just not possible at this point. Like, even I found out that there's always a way to hack into something, and even if like the thing is not connected to any cloud or like anything, it's just not any it's not connected to anything, just a piece of hardware that's running its own code, its own thing, it's still hackable. There's like still ways you can be hackable. So to prevent being hacked is definitely a problem, and I don't think it has a solution yet. Like being able to be unhackable, that's like a very big problem too, because essentially like let's take into this scenario into let's take into account this scenario. Let's say kidnapping, let's say that, right? Someone wants to kidnap you today. They have to actually like physically get out of your car, grab you, put them in your car, and that sort of thing, right? In a world of self-driving car, they would all they have to do is hack into your car and change the destination and lock the car, right? You can't do anything about it. You literally can't do anything about it. And so that is a very big problem. Like being able to hack into self-driving cars is a very big problem. I think that's going to be one of the big problems that we would have to solve in order for self-driving cars to actually help us instead of creating more problems, right? And I guess there's ways, I guess, like research kind of goes into this, like cryptography. I think like quantum cryptography and that sort of thing. Yeah, that is scary. That's definitely a possible scenario. And I don't think that's going to be like being able to stop people from hacking into cars. I don't think it's going to come anytime soon. feels good. There's like a lot of research kind of going into this, going into like quantum computing, quantum cryptography, and that sort of thing. So hopefully we're able to stop that before self-driving cars become like everyone's using self-driving cars. Hopefully we can solve the problem of hacking before that occurs. Because I mean, even if you think about it in Tesla's case, you see how many cars Tesla has like out on the street these days, and Tesla has like all their stuff is through like cloud. So all their like computing and stuff is done through cloud. So all cars are connected to Tesla cloud. The problem with that is if someone is able to hack into Tesla's cloud architecture, right? They could essentially control every single Tesla vehicle that is on the road, and that is a scary scenario. That is a very big problem, and we definitely need to look into cybersecurity in order to make sure um, that self-driving cars are actually safe and they actually solve like our problems instead of creating more problems. Yeah, great question. If you have any more questions, let me know. Oh yeah, also you guys can always like reach out to me. Like I dropped my LinkedIn on the introduction channel. You guys can always like reach out to me if you guys ever need help with um like finding opportunities for like self-driving cars or like just stuck in some problem and that sort of thing. Feel free to reach out to me. Yeah, I definitely reached out to a lot of people in order to I definitely reached out to a lot of people in order to learn more about self-driving cars and that sort of thing. So yeah, feel free to reach out to me.